Hello everyone! What we're going to be doing today is going through all the multiple choice questions in one paper in particular, and this is OCR's Breadth in Physics from June 2018. One way you could use this video as an independent learning resource would be to be pausing this video, attempting those questions independently, and then checking with the solutions straight after that. So let's get started with question number one. Question number one, the graph below shows the variation of displacement s with time t for an object. At which of those points does the object have a maximum velocity? Now, the steeper the gradient of the tangent of this curve, the greater the velocity, because in this case, the gradient of the tangent is going to indicate the velocity. So we're looking for the steepest point. So we can see that definitely point B has the steepest gradient if we were to draw a tangent around it. So I'm going to go for my answer would be B, which in this case is also the correct answer. Okay, well, let's have a read through question number two. Which definition is correct and uses only quantities rather than units? So it needs to be both correct and using only quantities. First one, A, acceleration is the change in velocity per second. Well, second is a unit, so it's not going to be A. B, resistance is potential difference per ampere. Well, this is also wrong because the amp is a unit. C, intensity is energy per unit cross-sectional area. That does not use units, however intensity is power per unit cross-sectional area, so this is not correct. And finally, D, electromotive force is energy transferred per unit charge, which is correct, and it also uses just the quantities rather than the units themselves. So in this case the correct answer is D. Okay folks, now let's have a look at question number three. A ball is thrown through the air, the ball experiences a small amount of drag compared to its weight. At a particular time, the ball is at point X, and point X is shown here. Which arrow best represents the direction of the resultant force when the ball is at that position? Okay, well, anytime we need to find the resultant force, what we are going to need is to draw all the forces acting on it. There's only two forces, one of them is drag, the other one is weight. Now the ball is actually moving along the tangent path, along here. This over here is the direction of motion. Now a common misconception here is that sometimes that there always is sort of a force pulling in the direction of motion, but that's not the case. In fact, there's a force in the opposite direction because this is the point at which drag is acting. So I'm going to draw all my forces here using my yellow marker, and there's going to be a drag force just over here, and I'm just going to call that F drag. There's also going to be a force pulling this ball vertically downwards. This is of course the weight, which is considerably bigger in this case over here. So this is the weight. Now, due to the process of elimination, we can already actually find the correct answer because we can see that A is acting just where, sort of very close to where the drag is acting, so it's not going to be A. C, the weight is not just the only resultant force, it's not going to be C, and it's definitely not going to be D along the direction of motion. So by the process of elimination at this stage, to save some time for the exam, the correct answer has got to be B. If you are really interested, as you should be, in the actual physics behind it, we can also just add those two vectors, the drag force and the weight force vector. The first thing we need to notice is that they're not quite tip to tail, so what I need to do is just move my drag vector just down here, like so. Then the resultant vector is going to be along this upper line, and I can sort of approximately draw this let's draw the resultant one in red somewhere along this line over here. So this is our resultant vector, which in this case is v. Right, let's move on to question number 4. Okay folks, now let's have a read through question number 4. An object is traveling to the right with a momentum of 40 kilograms per meter second. So let me just do a little drawing over here. So we have this object P, which is traveling to the right over here, and it has a momentum of 40 kg ms to the power of -1. Now that collides with another object Q, which is traveling to a left along the same path, so it's a head-on collision. So we have another one here which is traveling with some unknown momentum along to the other side. The final momentum of P, so after those two objects collide, P is going to be still moving to the right with a momentum of 10 kilograms meters per second. What is the change of momentum in Q? Okay, well, this is definitely going to be a conservation of momentum problem. So conservation of momentum. I'm going to do this in quite a lot of detail for explanation purposes. However, in an exam, I would encourage you guys to work methodically, but maybe don't write everything out in as great detail as possible. As long as we work methodically and reach the correct answer with multiple choice questions, time management is actually quite important. So let's go through this. The total momentum before is going to have to equal the total momentum afterwards. So let's say that the momentum of P before, I'm going to call that P1, plus the momentum of Q, so I'm going to call that Q1, is going to equal the momentum of P after the collision. I'm going to call that P2 really, and the momentum of Q after the collision, call that PQ2. Okay, so what's the momentum of object P before the collision? That's 40. We don't know what the next one is, like so. We know that the momentum after the collision for object P is 10 plus PQ2. Okay, well, we can already get a good estimate for the change of momentum of this object if we just do a little bit of rearranging. So I'm going to say that 40 minus 10 is going to equal PQ2 minus PQ1. Well, if you think about it, this quantity on the right hand side just here, that's actually the change of momentum in Q. So just write that. So 40 minus 10, that is equal to 30. That is actually the change of momentum of Q. So in this case, the answer has got to be 30 kilograms meters per second. So the answer is C. Okay folks, now moving on to question number 5. A wire P has length L, diameter D, and a resistance of 1 ohm. Another wire Q is made from the same metal, has the length 3 times the length and twice the diameter. What is the resistance of the wire Q? Okay, well, the first thing we need to do is look into our formula sheet and write down this equation that the resistance is equal to the resistivity multiplied by the length divided by the cross-sectional area. I'm just going to expand this a little bit further. So this is going to equal rho times L divided by the area, which is pi d over 2 squared. I'm even going to expand through the brackets. So this is going to equal rho L pi d squared over 4. Okay, well, let's see what happens next if the length of the wire increases 3 times. So if this guy here, the length Oops, that's my rainbow pen. Let's just use a normal red pen. If this increases 3 times, well, this is directly proportional to the resistance, so the resistance will also increase 3 times, like so. However, if the diameter increases twice, we're actually going to get a reduction of a factor of 4, and this is because the square applies to this reduction in diameter. Can illustrate this, so there will be an additional factor of 2d squared, which will actually give you a factor of 4. So if we double the diameter because we're squaring it, we're actually going to get a factor of this increasing by a factor of 4. Well, notice that R and D are inversely proportional, and if they're inversely proportional, if D increases by a factor of 4, R is going to decrease by a factor of 4. So overall, you can write this over here, overall R decreases by a factor of 3/4. The 3 comes from the length increasing 3 times. The 4 comes from the diameter increasing by a factor of 2, but then you're squaring it, so you're getting that factor of 4. So 3/4, which is 0.75. So the correct resistance for wire Q is going to be A. Oops, let's try again writing this. It's going to be A. Just for completeness, I'm just going to say that 3/4 in this case is 0.750 ohms up to 3 significant figures. Look at question 6. We've got 2 filament lamps X and Y are connected in series with a 16-volt power supply. There's no internal resistance to worry about in this question. Lamp X emits a power of 2 watts and lamp Y emits a power of 6 watts. What is the potential difference across lamp X? Okay, well, the first thing we need to sort of keep in mind here is that those 2 circuits are connected in series, and the current is going to be the same throughout the whole circuit. Well, let's try and answer what is the total power dissipated in the circuit. If bulb X emits 2 watts and bulb Y emits 6 watts, then the total power in the circuit, let's say the total power is actually going to be 8 watts. We can just use then the total power is going to equal to the current multiplied by the total potential difference. So we can just say that P total is equal to IV, where V is the total potential difference. So I'm just going to put in a little subscript there as well. The total power is 8 watts, 8.0 to be absolutely precise, multiplied by the current, multiplied by the total voltage, or total potential difference across this circuit, which is 16. That's fine, and now we can just rearrange for I, and if we do so, I is going to be 8.0 divided by 16, which is going to give us half, so 0.50 amps. Perfect. Now that we have the current through both bulbs, we know that there's going to be a current of 0.5 amps going through both of them. We're looking for the potential difference across lamp X, so we can just say that the power dissipated across lamp X is going to be equal to the current in the circuit multiplied by the potential difference across it, which is Vx. We know what the power is, we know what I is, so we are in business. The power across this bulb is 2.0 watts. That's going to equal 0.5 amps multiplied by the potential difference that we're looking for in this case? Well, let's just rearrange for the potential difference, which is going to be 2.0 over 0.5, which is going to give us 4.0 volts, which is the correct answer in this case. So the correct answer is B, 4.0 volts. Now question 7. Two resistors of resistances 2 ohms and 4 ohms are connected in series across the terminal of a cell of EMF 1.4 volts and internal resistance 1 ohm. What is the potential difference across the 2 ohm resistor? Okay, well, anytime we have internal resistance, it's also worth just writing down the formulas that we know. They're also given in the OCR formula worksheet. Well, we know that our EMF take away our potential difference, or terminal PD, is going to equal IR, where this lowercase r is the internal resistance. In this case, we're not given the terminal PDV though, so what I'm going to do is I'm just going to rearrange for the EMF, and that's going to equal IR plus V, and in fact we can just write this as IR plus the current multiplied by the total resistance in the circuit. So in this case, this lowercase r, that's just your internal resistance, which is just 1 ohm in this case, and this capital R, that's your sort of 6 ohms total resistance, the 4 ohm plus the 2 ohm. A different way of writing that is just I R, what happened there, let's try again, R plus R, just factorizing. Well, given that information that we have, we can now find out the current in this question, simply because we are given the EMF and we're given the total resistance and the internal resistance, R plus R. So our EMF is 1.4 volts, so 1.4, and we're going to be dividing that by R, which is our total resistance. It's going to be 4 plus 2, which is 6 ohms, and our internal resistance is given in the question to be 1 ohm. So this is actually going to equal 1.4 over 7, which is 0.2 amps. Okay, we have the current in this series circuit, so we're in business to find the potential difference across the 2 ohm resistor. So we have the current and we have the resistance of that resistor. We can just apply Ohm's law across this resistor now. So just for detail, I'm going to write across the 2.0 ohm resistor. Remember, when you're solving multiple choice question exam situation, don't go into as much detail. I'm just doing this for explanation purposes right now. So we can just simply apply the good old V is equal to IR, and we know that the current in this case is 0.2, and the resistance across it is 2.0 ohms, which is going to give us 0.4 volts. It's going to give us 0.4 volts. Perfect. So that leads us to a correct answer of A. And moving on to question number 8, we've got a student trying to determine the power P in a resistor. The measured values in the current and the resistance are given. We've been given the equation P is equal to I squared multiplied by R used to calculate P. What is the percentage uncertainty in the value of P? Now in this case we are multiplying quantities, and if we are multiplying quantities, what we need to do is add the percentage uncertainties. Now something which is really important is, because we have this I a factor of I squared, I'm just going to write this over here on the side, but the percentage uncertainty in I squared is actually equal to twice the percentage uncertainty in I. If this is new to you, or if you don't remember it quite well, I recommend browsing through the channel and finding my percentage uncertainties video, in which I've explained this in quite a lot of detail. Okay, well, let's find the percentage uncertainty in P. Well, this is going to equal twice the percentage uncertainty in I. And if we remember, the percentage uncertainty is plus or minus the absolute uncertainty, which is 0.2, divided by our value, which is 4.0, times 100, like so. And to that, we need to add the percentage uncertainty in R. We don't need to multiply by a factor because it's not R squared or R cubed or anything like that. It is simply R, so the percentage uncertainty in R is going to be 0.3 over 3.0 times 100 once again. So this over here, that's just equal to 10%, and the one on the right, that's also equal to 10%, or we could just input anything into a calculator just to be sure, but the correct answer is B, which is equal to 20%. So the correct answer is B, 20%. Just for the sake of completeness though, I'd just like to be extra clear and just to say that this quantity over here, this is our percentage uncertainty in I squared, twice the percentage uncertainty in I. I can just write that, twice the percentage uncertainty in I. And this quantity over here, well, this over here is your percentage uncertainty in R. Right, folks, we're making excellent progress. Moving on to question number 9. The diagram shows a uniform rod at rest in a horizontal position. It is hinged at point X. A cable is attached to a vertical wall at the midpoint of the rod. Which arrow best represents the direction of the force on the rod at point X? Okay, so we have to be really careful with the wording here. They're asking us for the force on the rod, not on the wall. And it's at point X exactly. So at point X, which is just over here. Well, the forces balance is actually really interesting. So let me just make almost a little diagram over here. So this over here is point X. We've got the cable, which is kind of pushing things upwards. Now this provides some tension. So it's going to have this tension is going to have some vertical component, which will actually cancel out the gravitational component. So this upward tension vector component is what's keeping this rod from falling down from the ground, because this vertical component of the tension is actually going to cancel out the vertical component of the gravity. Now the tension will also have one more component, which is going to be pushing the rod and applying a force onto the wall to the left. But remember, because of Newton's third law, the wall is going to push back on the rod in the opposite direction. So the only unbalanced force is going to be the horizontal force, and it will be the wall pushing on the rod with a direction to the right in this case. So the correct answer is C, which is purely to the right. Okay folks, moving on to question number 10, the halfway point. We have a car which is driven at constant velocity until the driver sees an obstruction ahead of time, t is equal to 0. The velocity against time graph below shows the motion of the car as it brings it to a stop. The thinking distance is 10 meters. What is the stopping distance of the car? Okay, well, the very first thing I'm going to write down here is that my stopping distance is going to be the sum of the thinking distance, which I'm going to call dt, plus the braking distance, which I'm going to call just db. Now I'm given that the thinking distance is 10 meters, so that's represented by this graph over here. Now I notice that there are no units or numbers on the y-axis, but we can actually figure those out. We can see that just where the driver applies the brake is just about over here at 0.5. Now, because the thinking distance is 10 meters, that's actually the area underneath this graph, isn't it? So that means that the velocity right at this point here has got to be 20. So that will give us this sort of red area to be 10 meters, because 20 times 0.5 is going to give us 10. Okay, well, let's add on to that the braking distance, which is going to be this area over here, this yellow area, this one over here, and that seems to finish at 2.5, like so. So the time that it acts on the x-axis is 2 seconds in total. So from here to here is 2 seconds. So this area over here, should we just write that? We can find that just using the formula for the area of a triangle, which is half base times height, which is a half, times the base, which is 2, multiplied by the height, which is 20, like so. That's going to be 10 plus 20, which is going to give us 30 meters in total. So the correct answer in this case is B, 30 meters. Moving on to question 11. A javelin thrower exerts a force of 100 newtons on a javelin for a time of 0.3 seconds. We have the mass of it being 0.8 kg. What is the rate of change of momentum of the javelin? Now, this is actually a crucial question, and the reason for that is because there's a trick in it. Now, rate of change of momentum is actually delta P over delta T. Let me just remind you that by writing Newton's law, which is that the net force of an object is equal to delta P over delta T, the rate of change of momentum. So this whole right hand side over here, this whole sort of quantity, this is actually what your rate of change of momentum is. It's not just the upper part of the fraction, so that's the rate of change of P. So this is actually going to equal to the net force. Now in this case the net force is 100 newtons. You could also argue that you have to subtract the force of weight, but in this case that will actually be quite low because it's just 0.8 multiplied by approximately 10, which is approximately 8 newtons, which will give you a resultant force of 92 newtons. But for this purposes, the rate of change of P is at least up to one significant figure is equal to 100 newtons. So this is your delta P over delta T. So the correct answer is C. So let's write this down. Okay folks, question number 12. One end of a wire is fixed to a ceiling and a 3 kg object is suspended from its other end. What is the diameter of the wire? What is the tensile stress in the wire? Well, the formula for stress is the force acting on the material which is being stretched divided by the cross-sectional area. Now in this case the only force which is acting is the weight of that object, so it's going to be mg divided by the cross-sectional area, which is pi times the diameter over 2 squared. Okay, well let's add in some numbers. The mass of the object is 3 kilograms. G on planet Earth is 9.81 meters per second squared, and we're going to divide that by pi. Now we have to be quite careful with the units here. The diameter is 0.62 millimeters. It's going to be 0.62 times 10 to the power of minus 3 divided by 2, and then all of this is squared. So we have to be quite careful how we input this into our scientific calculator, and if we do this correctly, we're going to get approximately 9.7 multiplied by 10 to the 7 pascals, which leads us to the correct answer being D. Okay, moving on to question number 13, guys. The intensity of light incident on a light dependent resistor is increased, its resistance decreases. In other words, we've got the classic graph of resistance against light intensity, which has a shape sort of similar to this. So in other words, as we increase the light intensity, the resistance decreases. Which statement gives the correct reason for this behavior? Why is this occurring? A, the cross-sectional area of the LDR decreases. Absolutely not. The cross-sectional area, I'm afraid, does not change. B, the mean drift velocity of the charge carrier decreases. That's not also true. We have a formula, the Nave equation for the drift velocity, and there is no mention of light intensity in that formula. C, the number density of the charge carriers increases. This is actually the correct answer. It's very, very interesting, but what is actually happening is that light is actually freeing up more of these charge carriers, and if there's more charge carriers, that means that there is higher current, and if there's higher current, well, that means that there's going to be lower resistance. So lower resistance. Just for completeness, D, the magnitude of the charge on the charge carrier increases. That is absolutely not true as well. In fact, the magnitude of the charge on the charge carriers is one of the biggest constants in the universe. You know, a single electron will always have a charge of 1.6 times 10 to the power of minus 19 coulombs. So in short, the correct answer here is C. Question 14. The total energy gained by 20 electrons traveling through a potential difference V is 30 kilo electron volt. What is the potential difference in volts? Okay, well, if the potential difference for 20 electrons is 30 kilo electron volts, then let's just write down the energy for a single electron. So for one electron, this electron would have gained 30 divided by 20 kilo electron volts, keV, which is just 1.5 kilo electron volts. Well, we have to remember though, what is actually an electron volt? Remember, an electron volt is the energy acquired when one electron volt in particular is the energy acquired when an electron passes through a potential difference of 1 volt. Well, that means that if the electron has acquired 1,500 electron volts, that means that it has to have passed through 1,500 volts. So in this case, the correct answer is C, 1,500 volts. Okay folks, question number 15. Trolley of mass 1 kilogram is moving on a horizontal surface at a constant velocity of 2 meters per second. A force of 3 newtons is applied to the trolley in the opposite direction to its motion for a time of 1.5 meters per second. Then the force is removed. Okay, well, let's draw this. The first thing to do would be just to draw this trolley. So let's say that this over here is my trolley, and let's say that it's moving to the right at a speed of 2.0 meters per second. We apply a force to it, which is going to be to the left, opposite to the direction of motion. That force has a magnitude of 3.0 newtons. I'm just going to write that as minus 3.0 newtons, and just for the sake of consistency in the direction, if something in this question applies with a direction to the left, it's going to have a minus sign. If something has a direction to the right, it's going to have a plus sign. What is the magnitude of the final momentum of the trolley? Okay, well, if we're linking forces and momentum, we're going to have to use Newton's second law. And that is that the net force on an object, let's say, let's call that F, that's going to equal to the rate of change of momentum. Let's figure out by how much has the momentum changed. So delta P is going to be F multiplied by delta T. So our change of momentum is going to be our force, which is minus 3.0 newtons, which acts for a time of 1.5 seconds. So it's going to be times 1.5, which is going to give us minus 4.5 kilograms meters per second for the change in momentum. Now remember, our delta P, that's simply equal to P final minus P initial, like so. So if our change of momentum is minus 4.5, we don't know yet what our final momentum is, minus the initial momentum. Well, that we do know, because the initial momentum is, I'm gonna write this over here, P initial, that's simply the mass times your initial velocity. Now if the mass is 1 kilogram and if the initial speed is 2 meters per second, so that is going to give us a value for the initial momentum of just 2.0 kilograms ms to the power of minus 1. It's going to be minus 2.0. Okay, well, we can rearrange for P final. So the final momentum is going to be minus 4.5 plus 2.0. We need to be really careful with the minus sign in this case. So minus 4.5 plus 2.0 is minus 2.5 kilograms meters per second. Well, hang on a minute, that's not actually any of the answers, but upon closer inspection we can see that the question is asking us about the magnitude of the final momentum. So the magnitude of the final momentum is 2.5. However, it is acting on the to the left in this case, which is taken to be the negative side. So the correct answer is B. Okay folks, moving on. Question number 16. The current at a point in a circuit is 10 milliamps. Expressed on the nearest power of 10, how many electrons pass the point in 10 seconds? So the actual charge that goes through is going to be I multiplied by our change in time. Our current is 10 milliamps, so that's 10 times 10 to the power of minus 3, multiplied by the time, which in this case is a further factor of 10, or 10 seconds. If we just multiply this out, so those two tens over here, that gives us a factor of 10 to the power of minus 2, 10 to the power of 2, sorry, multiplied by 10 to the power of minus 3, that's going to give us 10 to the power of minus 1 coulombs. Well, let's work out the number of electrons. So remember the, what happened here? Let's try again. The number of electrons, I'm just using this, this doesn't mean hashtag electrons, it just means number of electrons is equal to our charge divided by the electron charge, which in this case is going to be 10 to the power of minus 1 divided by the individual charge of 1 electron, which is 1.6 times 10 to the power of minus 19. Now if we put that into a calculator and we divide those out, we're going to get 6.25 times 10 to the power of 17. So let's have a look at our answers. Expressed to the nearest power of 10, how many electrons pass through that point in 10 seconds? Well, it says expressed to the nearest power of 10. Our answer was 6.25 multiplied by 10 to the 17. So the closest power in this case is C, 10 to the 18, with correct answer being C. So, moving on to question number 17. EM radiation is incident on a metal. The radiation has a wavelength, constant wavelength, with each photon having an energy of 5 electron volts. The work function of the metal is 3 electron volts. Which of the following cannot be, and I'm just going to underline this, the kinetic energy of the emitted electron? Well, remember the formula for this case is that the energy of a photon is equal to the work function plus the maximum kinetic energy. And the bit where it says maximum kinetic energy is critical for this question. Let's just rearrange for that because we're looking for the maximum kinetic energy. So K max is going to equal the energy of the photon minus the work function. So our maximum kinetic energy is going to be 5.0 minus 3.0, and that's going to equal 2.0 electron volts. So this is actually the maximum kinetic energy. No energies higher than that are allowed for the electrons which are escaping the surface. Now looking at A, B and C, the only number above that is D, so that has to be the correct answer. So correct answer D, 3.0 electron volts. Question 18. The waves emitted from two sources are coherent. Which quantity must be constant for these waves? Well, remember, two coherent waves, they actually have a constant phase difference. So this is one of the definitions that we definitely need to remember, that two coherent waves will have constant phase difference. So the correct answer is D. Almost there. Question number 19. The diagram below shows a stationary wave pattern for a sound wave in a tube. The tube has one open end and one closed end. We've got the length of the tube is 60 centimeters. What is the wavelength of the sound? Okay, well, one critical thing to remember in this case is let me just draw a wave over here. The distance from a node to an antinode is actually equal to a quarter of the wavelength. So this is really important. Okay, well, let's apply this. That if we have a node here and an antinode here, that means that this distance here is a quarter of the wavelength. This distance here is also a quarter of the wavelength. Finally, the distance from here to the end of the tube is also a quarter of a wavelength. Well, looking at this diagram over here, we can clearly see that the whole length contains 3/4 of the wavelength. So we can just say that 3/4 of the wavelength, or 3/4 lambda, are actually equal to 60 centimeters. So that means that the wavelength is going to be 60 multiplied by 4 divided by 3. So 6 times 4 divided by 3 is 80 centimeters. So in this case, the correct answer is D, 80 centimeters. Okay, folks, let's have a look at the very last question of this paper. What are the correct base units for work done or energy? Well, let's have a look at work done. Work done is equal to force multiplied by distance. And that is the case when the force is actually in the same direction as the direction of motion. Otherwise, we need a factor of cos theta. However, cos theta is also unitless, so we can happily omit this at the moment. Force, that is equal to ma multiplied by distance. Well, let's have a look at the units of this. The mass, that's measured in kilograms. Acceleration is in ms to the power of -2, multiplied by distance, which is measured in meters. So the base unit for work done is going to be kilograms, meters squared, because we get a factor of meters, times 100 meters, s to the power of -2, which leads us to a final answer of D, kilograms, meters squared, s to the power of -2. Okay, folks, we have solved the multiple choice question of the multiple choice question part of OCR's Breadth in Physics from June 2018. If there are any questions on the questions, please drop a comment down below or drop me an email.